Hi everyone. Today we're going to talk about the most basic concepts regarding related rates. Eventually these are going to turn into some pretty complicated problems that are used to model situations. This video is just meant to show the basic things that have to go on in these problems out of the context of a modeling situation. We're going to assume that x and y are both differentiable functions of t, and we're going to find the required values of dy dt and dx dt. What we're going to have to do, in fact, is differentiate these functions implicitly. Just like in section 2.5, where every time you differentiated y, you had to use the chain rule and put dy dx. Since we're going to be differentiating with respect to t instead of respect to x, we're going to have to use the chain rule every time we differentiate x and y. So, our function of time for this first problem is 4y squared plus x squared equals 4, which if you divide out everything by 4, you'll notice is an ellipse. Given that dx dt equals 2, we need to find dy dt when x equals 1. So, the first thing we need to do is differentiate with respect to t. Capital WRT is a common abbreviation for with respect to, so I'll use that sometimes. And so by using the power rule, derivative of 4y squared is 8y. And then, because we're differentiating with respect to t, I need to use the chain rule and multiply that by dy dt. Again, what that means is I'm differentiating the variable y with respect to the variable t. I'll do the same thing, do the power rule with x squared. So that'll be 2x, and again I'm differentiating x with respect to t, so I need to put a dx dt, and then the derivative of 4 is just 0. Notice right now there are 4 variables that are unknown, but we only know 2 of them. Well, one of the things is we'll have to look at the implicit function and figure out what the y value is when x equals 1. So by substituting x equals 1, we get the equation 4y squared plus 1 equals 4, and can solve that for y. So I subtract 1 from both sides, divide both sides by 4, and then take the square root, and y can be positive or negative 3/2. And now we just need to substitute all the values that we know and solve for the unknown. If y equals positive square root of 3 divided by 2, then we can substitute that for y, substitute 1 for x, and substitute 2 for dx dt. So I have 8 times square root of 3 divided by 2, which I could also write as 4 square root of 3 dy dt, plus 4 equals 0. And by subtracting 4 from both sides and then dividing both sides by 4 square root of 3, you get that dy dt equals negative 1 divided by the square root of 3. Notice that for the other case, if y equals negative square root of 3 divided by 2, you're just going to get positive 1 divided by the square root of 3. One more comment I want to make about this. So we were given in the previous slide that dx dt was positive 2. So we want to look at the fact that the x value is increasing as time increases, which you can see is happening as I draw the red arrow. Notice the direction of the y, though, is going down. So at the point 1 square root of 3 divided by 2, it should make sense that the dy dt, the change in y with respect to time, would be negative. And same thing here, when we were looking at the point 1 comma negative square root of 3 divided by 2, as the x is increasing here, again because the change in x with respect to time was positive 2, it should make sense that the change in y with respect to time is positive, because at that point the y values on the curve are increasing. So, one more basic, kind of out of context problem. So a point is moving along the graph of the function y equals x cubed, such that dx dt is 2 centimeters per second. We need to find dy dt if x is equal to 10. So same as before, we need to implicitly differentiate y equals x cubed with respect to t. And so by doing the power rule, derivative of y is just 1, and then times dy dt by the chain rule, and then do the power rule. So derivative of x cubed is 3x squared, and by the chain rule, since we're differentiating with respect to t, we have to multiply that by dx dt. And now it's just a matter of plugging in what we know and solving for our unknowns. So I'll just get rid of that 1, because 1 times dy dt is just dy dt. I'll substitute 10 for the x, and I'll substitute 2 for dx dt. And so I find that dy dt is 600. Again, if we take a quick look at the graph of y equals x cubed, we can see as we go out to x equals 10, the curve is getting very, very steep. And since the dx dt, the change in x was positive 2, as x moves to the right over time, the y is moving up, and we can also see that the y is starting to change really, really, really quickly. So it should make sense that this number is quite large, that dy dt was 600. So this is the really basic kind of math just for the sake of math problems. What we're going to need to do now is actually use a lot of formulas we know from geometry and physics and lots of other places that we've encountered in our previous classes, and we'll need to actually come up with some of these equations on our own in order to be able to solve these problems.